Okay, fantastic. Dear Sue, may I ask you to please introduce Dr. Charlotte Toma?
Well, Morena, I have great pleasure in introducing you to a young woman we know rather well. First of our three creative daughters, Charlotte, as a brief resume, went to Remuera Primary, on to St Cuths and University, studying engineering, and did her PhD on seismic engineering. And just very fortunately at that time there was an earthquake cropped up in China, and then a notable one in Italy, and then of course one close to home here. So I was lucky enough to be the spell checker come editor for Charlotte's thesis, which is a book about this thick. I have learned a lot about in-plane structures, and the title of this beast is The Effect of Seismic Activity on Unreinforced Masonry. Who knew there was so much information for it? Anyway, Charlotte is a very gifted and talented young woman. She has got far to go, and we love her dearly. She will talk to you about inclusivity, diversity, inclusion, sustainable engineering obviously is the buzzword at the moment, and Charlotte, I'm sure, will give us an insight into the latest on that and the trend in the world. So without further ado, my lovely daughter Charlotte.
Thanks, Mum. It's lovely. I imagine at some point Karis might join me, so I'm quite used to having her on my hip, but we'll see how we get on. Morena, everyone, welcome. I will try and keep this to my 20-ish minutes, but I'll warn you, as a lecturer, we're quite used to filling up the hour, so I might get carried away. Today I'm going to talk about drivers for change. The work that I am involved with is structural engineering, and in New Zealand that's heavily seismic focused. Although my focus at the moment is on how we connect seismic engineering with sustainable engineering, as that's where we really need to be heading with climate change, but also with the regulatory drivers that we have in New Zealand. So I've got my name up there, but I've also got my colleague Max Stevens, as we recently presented on this work at the New Zealand Society for Earthquake Engineering Conference, and together we supervise our PhD student Rosa Gonzalez, so it's the three of us up there. So as engineers, you can't hear me? I hate microphones. As engineers, we're often faced with change, so we have to adapt to changes from the architects, the clients, pandemics, price changes on site. And I'd say that as a profession, we're pretty good at dealing with change. I thought it should come. and being innovative problem solvers. However, I believe that there are areas that, as engineers, we are quite stubborn to change. And as my parents will know, I've spent a long time railing against the diversity issues that we have in engineering. As females, we're less than 13%, and we're stuck at that place. But today I'm not going to be talking about that. I'm going to be talking about sustainable engineering. So the change needed to achieve the net zero carbon goals is often talked about as needing a paradigm shift in the way that we do things. Disruptive thinking even, which to date has not been that warmly embraced by my industry. At the same time, we are talking about significant changes in the way that we think about seismic hazard. We're thinking about how we adjust the seismic design philosophy, which we've actually been working with for over 60 years. The society is demanding better seismic performance in our infrastructure and buildings, better functionality after an earthquake. So my goal here today is to show you that we can link these two things. If we can link seismic resilience with sustainable design, then we can move forward with the design challenge. So just stepping back for a moment, taking this back to a why. Why as a construction industry do we need to be thinking about sustainable design? Well, the really turning point was the IPCC report that was issued in 2018. This report set out very clearly there's differences in the world if we aim for a 2 degree or allow for a 2 degree temperature shift versus the 1.5 temperature shift. The words that they were using in this report, rapid, far-reaching, unprecedented changes that are required, these are unambiguous, these are strong language, and up until that date, the scientists really hadn't been using this language. They'd been very cautious, and there'd been a lot of concern about not wanting to seem overly dramatic about climate change. But it's not the case anymore. We've moved on from this point. And in fact, it's a bit hard, it's behind me, but this graph here is showing us the annual billions of tons of carbon dioxide that we emit over the lifetime of the history of humanity. And we can see that currently we are emitting the most that we ever have, right at the top of this point. And you can see that it really hasn't adjusted since we've had the Earth Summit, the Kyoto Protocol, the Paris Agreement. None of these things have actually adjusted how much carbon that we are emitting into our atmosphere. But key to this graph is that although it's gone up hugely, it now needs to go down drastically. So how are we going to achieve this? This 50% target by 2030 seems a daunting task. But it's critical that we do aim to, or we strive to hit this intermediate goal. So what we're seeing on this graph is the bottom green line. If we do aim for this 50% reduction by 2030 and then target the net zero by 2050. If we still hit net zero by 2050, but we don't aim for this intermediate target of 2030, we're kind of along this protected orange line up the top. And the area under these curves is the total carbon dioxide that we'd be emitting in that time. So what you're seeing is that if we follow the orange line versus the green line, in that next 30 years we'll be emitting twice as much carbon dioxide into the atmosphere. Globally, the built environment accounts for around 40% of carbon dioxide emissions. So as an industry, we have a really strong role that we need to play. So just very briefly, where is the building and construction sector sitting in terms of regulation in New Zealand? Well, we know we have the New Zealand Climate Response Amendment Act from 2019, and this has set out our greenhouse gas emissions along with the emissions budget. And just recently, the government has amended those figures, and we're now aiming for or required to reach this 50% reduction of the 2005 emission levels by 2030 and net zero by 2050. If you follow all the legislation down and the policy, you will end up at the MB Building for Climate Change program, which is the building and construction sector's action plan for reducing emissions from the building and construction sector. Now, our sector in New Zealand is about 15% of the national emissions, so 40% globally, but New Zealand, our emissions distribution is a little bit different. So where do these emissions come from in terms of the building and construction sector? Well, we have a split between what we call operational and embodied carbon. So the operational carbon, is, if you see on the right, is really talking about our electricity generation, so what's required to operate the building once it's built. The embodied carbon is everything that goes into forming the building or making the building, so it's the practical materials, the transport, the construction, any emissions involved in building the building, as well as, I was going to say debuilding the building, deconstructing the building. So, what does this Building for Climate Change framework look like, and what does it require us to do as a sector? It's really key that in the sector we are looking at whole of life carbon. So to understand our relationship with carbon as a structural engineer, we can look at the life cycle about carbon emissions. Right, so we're talking about this life cycle of carbon. And I just want to clarify that when we're talking about carbon emissions, we're actually quantifying the greenhouse gas emissions that have a warming effect. These emissions have a range of impacts, and the global warming potential is just one of these. And we quantify that in equivalent kilograms of carbon dioxide emission. So very quickly, the life cycle is broken into 4 modules, which you will see in a moment. Oh, here we are. So we have module A that's associated with the manufacture and fabrication of the materials. So you can think of that as right back from the sourcing of the raw products, so it could be the quarrying and the mining, right through creating those materials and then through to transporting those to site. So we call that cradle to gate. And then we have module B, which is the operational emissions that occur during the life of the building. And there are some embodied emissions in that phase, but that really comes if you need any maintenance. And then we have module C, which is around the deconstruction of the building, and then finally module D, where we might make some savings from the recycling or reuse of materials at the end of the building life. So across these modules, the emissions are split between the embodied and the operational, and at the moment we understand these emissions split to be around 35% to the embodied carbon, 65% to the operational, but that is really shifting towards more of a 50-50 split. So if we have a look at this over the life cycle, we can see that our embodied carbon emissions have this really giant chunk that occurs right up the front. And we call that upfront emissions. That makes sense. It all happens right at the beginning. We can see that there are some embodied emissions over the life cycle of the building. And this really is the key to my talk, is that these emissions can be quite significant if our building is in a location of high seismicity. So the carbon footprint associated with the damage, repair and partial reconstruction, or in some cases the full reconstruction, can be a significant part of that total carbon. So these additional risks, like earthquakes, are not typically accounted for in our life cycle assessments. However, if we want to link seismicity to sustainability, we need to start accounting for the seismicity. This little pie chart here is showing how this split is changing between operational and embodied. So historically, the effects of buildings on climate change were only accounted for by looking at the operational emissions. And I think we're all quite familiar with this. We've seen the stars on your dishwasher. You know that you've been encouraged to use low energy light bulbs, you turn the lights off, etc., etc. But as now our energy generation is becoming less and less carbon intensive, the operational carbon of the building is becoming a lot less portion of the pie, and the embodied carbon, what the structural engineer is associated with, is becoming a lot larger piece of the pie. So just to summarise all of that, new buildings have around 2/3 of their upfront embodied carbon emissions associated with the structure. So, and we've seen that that is really associated with the production of the materials. So what we're saying is that we really need to decarbonise these materials. And luckily, perhaps, structural engineers really like to use very minimal materials. We work in steel, we work in concrete, we work in timber. A little bit of other things, but not too much. So if we can decarbonise these materials, then perhaps we can get a long way into reducing the carbon overall. Today's technology and materials, through really leading cutting-edge projects, has shown that we can reduce our carbon footprint by around 50% on our business-as-usual case. So that will get us most of the way to our 2030 goal. But in the terms of current technology, it's not going to get us to that net zero by 2050. So I just wanted to show you a little bit around what is happening with these materials and how we may get some traction in terms of heading to this net zero. So concrete here, this picture on the left is the percent of the emissions that comes out of a cube of concrete. And we can see that it's really heavily dominated by the cement. So the aggregate is only about 14%, and the steel, the reinforcing steel, around 20%. But the cement is the big bulk. And it makes sense because of the way that the production process of forming cement. So cement requires us to heat calcium carbonate to only over 1400 degrees Celsius. We can't achieve that with electricity, so we are burning fossil fuel. And also the chemical process of burning calcium carbonate actually releases carbon dioxide. So essentially we're undone. There's not really that much we can do in terms of the cement process. We can potentially use hydrogen as a source of fuel, but as we'll discuss in a moment with steel, green hydrogen, one, we're not making it as fast as we're going to need it, but two, there's a humongous demand across automotive, airspace travel, shipping, steel manufacturer that's going to want this green hydrogen, so it's going to be under huge demand. So what can we do? Well, we're going to be looking at cement replacement, essentially, and at the moment the options for cement replacement locally is fly ash and what's called granulated blast furnace slag, which is their byproducts of the steel industry and byproducts of burning coal, which we don't really do. So we've got these two cement replacements that actually come from very unsustainable industries themselves. And as Huntly closes down, we're not really going to have that fly ash anymore. And what we are in fact doing is importing it, which doesn't make a lot of sense, really. Another thing that we really need to be thinking about is that if the goal is to reduce emissions globally, then by us taking fly ash from another country where it would have just been used anyway, we're not really reducing emissions, we're just moving them around. So what else is going on in the cement replacement? In Switzerland, they've just developed or found the technology to develop calcined clay, so another natural resource that has pozzolanic materials and that we can use as a cement replacement. And they've trialled that, and we're looking at about a 30% reduction on emissions from the cement process. So that's fantastic. The problem is rolling that out into a large scale. There are some other kind of interesting niche innovations, such as actually injecting carbon dioxide into wet concrete, so it's like a carbon capture and storage system, burning sludge and waste rather than fossil fuel to power the burning of our clinker, so our cement. But we need to be careful that actually, on the face value, these provide very little carbon reductions, so understanding actually what they're offering us is really key. In the steel industry, there is two methods for making steel. The electric arc furnace, and the key on that is it uses electricity, and if we're decarbonising the electricity, that's good. However, it really only operates with scrap steel, and at the moment we are using 3 times as much steel as we have scrap steel, so we can never fully commit to electric arc furnace as the only way forward. Then we have the blast oxygen furnace, which uses iron ore, so where we mine the raw material. But to heat that iron ore, we use what's called a preheated coke in form of coal, so it's a fossil fuel. So if we can move away from that and move into the electric arc furnace, perhaps powered by hydrogen, then we'd still just need to find a way of using the electric arc furnace, but with a raw material like iron ore. So they're looking at ways to preheat the iron ore, to treat the iron ore using the hydrogen method and then put it into the electric arc furnace. And what's really exciting is that they have managed to do this, and they managed to produce a handful of steel, and obviously that's really not going to cut it. So these technologies are coming, but they're not yet here, and they're not ready to be upscaled to the level that we need. So what the steel industry in New Zealand is relying on at the moment is offsetting, so essentially planting lots of trees. And then we've got timber, which on the face of it looks great, and on the whole it is. There are other issues around structural uses of timber, being that it has a much lower structural strength, so we're not getting the spans. We're going to be building different types of buildings. And then we have issues around fire, so obviously timber and fire, not a great combination. So we're just working through all of these demands on timber. And the other key thing in the timber industry is that a tree planted is not equivalent to a tree cut down, because the grown tree is the one that is absorbing the carbon for us, and that's where we're getting the benefit out of the forestry, is that it's absorbing the carbon dioxide in the atmosphere. And that really doesn't happen until the tree is 10 to 20 years old. Then its absorption of carbon is rapidly increasing. Alright, so that was quite a lot of background. What I wanted to point out here is what would change if carbon drove our design as structural engineers. So we've talked about materiality. What we're really pointing at is building less, using less stuff. Do we need to build the building? Can we reuse the building stock that we have? So we're looking at repurposing, retrofitting. I worked with some engineers, student engineers, just last week who had a whole project about repurposing buildings. So walking around Auckland City, what structures weren't being utilised, even car parking structures as we move away from cars coming into the city, can we repurpose our car parking structures? Oh, and we really need to move away from this carbon offsetting. That's not going to be the answer. So hopefully you've gained from what I've been saying so far that the goal is to decarbonise. Sorry, I've got a person swinging on me down here. What we want to do is shift the curve, and it's just really a play on our life with COVID. Not your 1 p.m. briefing, but we are asking you to shift the curve. We need to reduce our average carbon footprint right down. Now, I just want to now start moving towards something a little bit more technical. The MB objectives for how we're going to reduce our footprint in structures has set out some objectives of how we're going to do that. So this is the Building for Climate Change program. And as structural engineers, we've picked up on a couple of these things that seem to contradict themselves in some spaces. This concept of lean design and increased resilience is quite counterintuitive to New Zealand-based engineers or engineers within a high seismicity space. So this graph over here, you're not going to be able to hear me, but I'm going to point. This is the hazard curve in the UK. So this is the kind of level of earthquake, this is acceleration that they would be designing for. This is the lowest hazard that we design for in New Zealand, and these are the highest hazards that come all the way up here. So when they're talking about lean design in the UK and optimizing their structures, they're in fact optimizing their structures for gravity loading. And the key to that is that there is really not a lot of uncertainty in gravity loading. We know what we're putting in our building. Where the uncertainty comes from is the seismic hazard, the seismicity. So New Zealand engineers like robust, we like resilience, we like additional load paths, and we don't want to optimize every member because we have this very high level of uncertainty. So what we're trying to say is that if we want more resilient structures, we really don't want lean design. So the work that we're doing at the moment is looking at, sorry, I'm going to stand right in a minute, what's the difference between a code design, so just a minimum code design, and above code design. And what we're saying here is that if you looked over the lifetime of the building, you might have this much greater increased carbon emissions with your code minimum building, assuming it has some, or experienced some earthquake over its design life. Oh, wrong way. So as that earthquake hits, you're going to be required to do maintenance and repairs, and you'll have this increased carbon. Versus if we build our buildings to a higher seismic level to start with, then over the lifetime, that additional carbon would be lower. So this is the concept of carbon risk. So what we're aiming to do is create this framework to assess the whole of life carbon over the building's lifetime, accounting for the seismic hazard and the structural performance. And what we're really asking is, are we able to justify a higher seismic performance and potentially a higher initial carbon? I want to do it myself. Based on this carbon risk metric. And if we reframe that phrase, you'll get my whole research world. Can sustainable design and low carbon design objectives align with the increased drive for seismic resilience at a community level? So that was kind of a little bit technical. Switch to something a little less technical, this motivation for change. So what we wanted to look at here was Christchurch a success? We're very lucky as earthquake engineers, lucky is the wrong word, but we have this great case study. We've seen it, we know what's happened afterwards. So we ask ourselves these questions, Was Christchurch a success? And as a structural engineer, the answer is probably yes. Our building code requires us to build buildings that preserve life safety. So the buildings that were built to the modern day standards, they did survive. They allowed people to escape. And yes, there were the exception of a really badly engineered building and buildings that were historical and weren't built to current standard and did collapse. But the modern standards, those buildings did achieve their objectives. If we ask that same question to society, was Christchurch a success? I think you'd say the answer was no. There was huge mental health and well-being issues, massive financial stresses at all levels, right from government all the way down through the insurance companies, through personal finances. And at the environmental level, we don't have to look very far for the demolition and the debris that was a result of Christchurch. And you can see here the extent of the demolition afterwards. So through a sustainability lens, social, financial and environmental, Christchurch wasn't a success. And therefore we have our driver for change right there. We know that we need and want better. So just to add one more point of why we need change, we did this study of quantifying the emissions from the demolitions in Christchurch. And we just focused this on a case study of 142 reinforced concrete buildings. We quantified all the waste from the demolition of those buildings, as well as all the emissions from reconstructing a building to create the city again, to replace those structures. And what we saw, well, there's a whole lot of figures in there, but the only real key part to this is that 90% of those buildings were demolished before their end of life. And the emissions that came from them was astronomical. So just from the 142 buildings that were demolished, that equated to around the emissions of 100,000 cars in New Zealand for a year. Now that only equated to about 10% of the commercial demolitions in New Zealand, so that would be, at a rough extrapolation, emissions of 1 million cars on the road for a year. That's the commercial building demolition at 1,200 buildings. Residential was 7,500. So we're not even close. So my last 5 minutes, I hope I haven't lost you all. But this really just gets to the research that we're doing, and this is the building the carbon case for resilient design. So I wanted to talk you through very quickly what this framework is and how we're going to justify moving away from the seismic design philosophy that we have at the moment. So it starts with just calculating the upfront carbon costs for a building. We have a baseline structure, and then we're going to redesign that structure for higher seismic performance. That might look like base isolation, it might look like stiffer, stronger, or it might look like where we're aiming for at the moment is low damage design. Essentially, can we create a structure that needs minimal repair in a serious earthquake? We model the structure, we put everything in there that we know on what we expect a building to perform, and then we submit it to a number of earthquakes. And in fact, earthquakes at a lot of different hazard levels or intensities, so just imagine that as earthquakes at different sizes. And these are all earthquake records that we have. So existing earthquakes, 30 different earthquakes run at 9 different hazards, 270 earthquakes we're subjecting these buildings to. And we then record what the performance results are of the building. So we're measuring accelerations and displacement, so how much the building is moving at those different earthquakes. And then we take all those damage markers, all those building response parameters, so the accelerations and the displacements, and we equate those to damage. So we can then say for different sizes of earthquake what the damage is likely to be for those buildings. And then we take that damage and we work out what the carbon emissions would be in terms of repairing those buildings, and in the worst case for fully replacing those buildings. I'm going to skip this part because it gets a little bit complicated. It's not probably needed. But essentially what we end up in the end is this annual carbon hazard. So how much carbon is this building likely to emit over its lifetime, taking into account the probabilities for different sized earthquakes occurring over its lifetime. And we can use that methodology to compare different design philosophies, so code minimum, above code, for different materials, etc. We ran a case study. We found that if we designed an above code building for just a stronger situation, it would equate to about 1.5% increase in the embodied carbon up front. But if we looked at the carbon over its lifetime, accounting for all these seismic risk, we're actually at a decrease of 6%. And that really doesn't take into account any of the other reductions in emissions that we've already talked about. So other things that we could be doing, like low carbon materials. And then finally, I just want to point out that we are looking at this for different materials, timber, concrete, steel. We're looking at it for different types of buildings. I've just got some funding from EQC to look at it for medium density residential buildings. And we also have a project looking at existing buildings. So is it going to be, in the carbon cost sense, more economical to retrofit this building and keep it for another 30 years, or demolish now and build something that is more sustainable now? And then just finally, so how big is our contribution? Here we go. Where have I lost all my pages? Left all my notes behind. So if you've been wanting to take a holiday between Sydney and Auckland, Auckland and Sydney, and you decided to stay at home and not take that flight, that's about 0.8 tonnes of carbon. If you decided to be a little bit healthy and you cut out beer, meat and dairy, goodness knows why, you would save 2 tonnes of carbon for the year. And if you gave up your car for a year, that would be about 3 tonnes of emissions. In a structural engineering sense, if we were to replace, I don't think you'd be able to read these, if we were to replace 80 steel beams with timber beams, so that could even just be one project, that's 27 tonnes of carbon. If we were to engage a geotechnical engineer and check the soil conditions, and we were able to narrow down and shrink down our concrete footings just for residential projects, over 20 different houses, that would be 163 tonnes of carbon. And what we're really aiming to do now is question the size of the buildings that we're building. Do we need 9,000 square metres, or can we make do with something a bit smaller? Can we optimise space? Can we use spaces for multi-use areas? So if we were able to take a 9,000 square metre building and argue that we can make do with a 10% smaller footprint, we could save around 400 tonnes just in one project. So I guess the point here is that as structural engineers, we actually have a massive role to play in the global reductions of carbon. So that's the end. Thank you for listening to me. I think that was really quite a lot for a Friday morning, but